Spacecraft thermal management systems play a pivotal role in ensuring the operational success and safety of space missions. These systems are designed to maintain temperature levels within spacecraft that are suitable for both human life and sensitive equipment, despite the extreme temperatures of space. As space missions grow longer and reach farther into the solar system, the demand for more advanced and efficient thermal management technologies becomes increasingly critical. The environment of space presents unique challenges for thermal management. In the vacuum of space, traditional cooling methods like convection are not possible, and radiation becomes the primary mode of heat transfer. Additionally, spacecraft are subjected to intense solar radiation on one side while facing the cold vacuum of space on the other, creating significant thermal gradients. Managing these extremes is crucial for protecting onboard systems and crew. Materials and coatings. The development of new materials and coatings that have superior thermal properties is fundamental to future spacecraft design. Materials that can reflect solar radiation and dissipate heat efficiently are being developed. These include advanced metamaterials that can control the direction of heat flow, and new types of thermal insulation that offer high performance in a compact form. Moreover, researchers are experimenting with phase change materials, PCMs, that absorb or release heat by changing state, which could provide passive thermal control without the need for power consumption. Active thermal control systems, ATCS. These systems use fluids to move heat from warmer to cooler parts of a spacecraft. The future of ATCS lies in optimizing these fluid loops to be more efficient and lighter weight. Miniaturization of components such as pumps and radiators is also a focus area. Additionally, there's a growing interest in developing variable conductance heat pipes and two-phase loops that can adapt their thermal conductivity based on the heat load, providing more efficient heat transport and dissipation. Electric and magnetic refrigeration. Spacecraft of the future might employ technologies like magnetic refrigeration, which uses the magnetocaloric effect to cool materials. This technology offers the benefits of having no moving parts, which reduces the risk of mechanical failure, and does not rely on refrigerants that can be harmful to the environment. Thermal energy storage. With the increase in the duration of space missions, especially those that may involve long periods in shadow, such as lunar or Martian surfaces, thermal energy storage becomes crucial. Thermal batteries that store heat when it is abundant and release it when required can help manage the thermal environment efficiently. This method is particularly useful for managing the cyclical heat loads during orbits that expose spacecraft to varying solar and shadow periods. Integration with structural elements. Incorporating thermal control elements with structural components of spacecraft is another promising area. This integration can lead to savings in mass and improvements in structural integrity. For example, structural panels that also act as radiators can reduce the weight and increase the space for other critical systems. Smart thermal management. Leveraging advances in sensors and control algorithms, smart thermal management systems can dynamically adjust to changing conditions in real time. These systems use data from thermal sensors distributed throughout the spacecraft to optimize heat distribution and dissipation, reducing the energy consumption of active cooling systems and improving overall system reliability. Radiative cooling techniques. Exploring advanced radiative cooling techniques that can effectively emit infrared radiation to the cold depths of space could enhance the passive cooling capabilities of spacecraft. These techniques involve designing surfaces that maximize emission at wavelengths that are transparent to the Earth's atmosphere, which could be particularly beneficial for near-Earth objects. Thermal management for power systems. As spacecraft power systems become more powerful to support advanced instrumentation and prolonged missions, managing the heat produced by these systems is essential. Innovations in thermal management for battery packs, nuclear reactors, and solar panels are necessary to prevent overheating and ensure efficient operation. The advancements in spacecraft thermal management systems are crucial for the success of future space exploration missions. These systems must not only be reliable and efficient but also lightweight and adaptable to various space environments. As engineers continue to develop and refine these technologies, the ability of humanity to explore deeper into the cosmos will continue to expand.